have the pleasure and the honor of opening this session. And I'd like to say a few words about Professor Neri Niccolai. And Professor Neri Niccolai was born in Florence in 1947, and he graduated in chemistry from the University of Florence in 1971. Shortly after graduation, in 1977, he spent 2 years as a research associate at the University of Wisconsin. And in 1985, he was visiting professor at the School of Pharmacy of the University of London. Neri, since year 2000, is full professor of biochemistry at the University of Siena, where he also supervises the laboratory of structural biology. He is the author of more than 160 scientific papers, with an H index of 26. Just a few words about his studies. He introduced many novelties in the field of bio-NMR, and we like to remember here his vast scientific production about the use of paramagnetic probes for the study of the surface of biomacromolecules. This technique has been proposed in one of its first applications as early as 1978 and has been much refined since. But as we all know, it is not sufficient to be a distinguished scientist to be awarded our gold medal, and actually one must also be committed to the development of NMR in our country. Neri has been very active in the past, and we remember the organization of several NMR schools in the 80s, and he is still very active now as he participates and actively participates in our social life during our meetings, very often with his fellows and co-workers. So for all these reasons, we are delighted to award the 2014 Joint Gold Medal GIDRM to Professor Neri Niccolai for his contribution to the science of NMR and for his commitment to our NMR community in particular. So many compliments. Neri, to you. The stage to him. Many compliments again.
It's a must for me to thank not only Mauro Cremonini for his very kind words about what I've done, but also I would like to thank all the executive board of GRM and GIRM for their decision. And also I would like to thank them because in this way I have the opportunity to talk about what I have done in the last 40 years. So a lot of time passed, and what I did in the meantime. The training in NMR, for sure, was one of my first interests, and I started with the colleagues in Siena in 1975, soon after we obtained the first instrument, among the first instrument, Fourier transport instrument in Italy, the WH90 megahertz Bruker. And we organized a course in 1975 about C13 FT NMR. And after that, we started a series of other GIDRM, without the I at that time, on training for magnetic resonance, most of them held in the charter house of Pontignano, very lovely place where professors and students were cooperating in very strict collaboration. And it's a pleasure also to have found two students of mine 1 hour ago during the lunch. They were present in the school of 1988, and that went on for all the 90. So this is as far what I have done the training section of my activity. And going to research, what I have done in these several years. Well, first of all, I would like to thank all the people who gave a contribution to what I have done, because I was not alone. I had a lot of suggestions, ideas, criticisms, and cooperation for collecting data, analyzing data, and in a very critical way. So I think that before going ahead, I must thank all of them. By the way, there are 4 other medalists among them. You might be able to recognize them. And it was a very big honor and pleasure to have such kind of cooperation. Oh, I must acknowledge also molecules, because what I have done was possible because I found very good model systems. These molecules, for one reason or another, had a very peculiar and very good NMR feature. Their paramagnetism, their structure stability, and so on. So, my activity, I can divide it in 2 periods. One, pre-nitroxide area, using parts, and that pre-nitroxide area, what I did, the use of manganese ion as a probe for investigating on biomolecular structure complexes, and after my permanence in medicine in Wisconsin, the use of multiple selective proton relaxation and nuclear overhouse effects. We were young at that time. It was not a routine technique at the moment. And from '79 onward, started my post-nitroxide era. And that was, the beginning was in a very humid and hot summer in August in Madison. And while we were fighting with mosquitoes, we set up a new kind of NMR approach. And because of this, I got a kind of famous, so that our past beloved president, Lucia Zeta, defined me as a temple uncle. So I should give credits to temple grandfather, Edmond Fremy, who developed and published, respective on the impact factor of that journal, Annals of Chimique and Physique, in 1845, a paper regarding stable spin levels. So what we have done in that humid summer was polluting the solution, the methyl sulfoxide at that time, with a soluble and stable nitroxide temple. And what we saw, observing the inversion recovery relaxation of gramicilinase, we saw that at the beginning the amide protons relaxed more or less at the same, with the same rate, but after we put nitroxide, we could distinguish fast protons which were much more speeded up as far as their proton relaxation was concerned, comparing to actually one, the leucine amide proton, because that proton was hydrogen bonded. The other hydrogen bonded valine was obscured by the aromatic ring at that frequency, 270 megahertz. So we realized that we had found a way for distinguishing hydrogen bonded protons from non-hydrogen bonded protons, and of course we thought that the application of this could be very, very, very important. The paper was published straight away on the journal, straight away in 1982. We were very lazy in writing papers at that time, and maybe also now. And so, after 10 years, we realized that since the nuclear relaxation was driving this kind of selection between affected or unaffected by the paramagnetic interaction, we realized that instead of be bound to one-dimensional spectroscopy and kind of inverse recovery experiment, we could expand our approach to n-dimensional spectroscopy, observing the attenuation of the signal induced by the presence of the paramagnetic probe. Of course, we presented what we did in the GIDRM conference. It was the 23rd conference in Cagliari, talking about the effects of the temple with lysozyme. And we presented that paper on BBRC and was rejected, saying that it was too preliminary, and unfortunately was accepted by someone else in biochemistry 6 months later. So, very disturbed by this fact, I went back to gramicylase, a very homey molecule, and I was able to publish in the Journal of Chemical Society in 1991 the experiment proving that we could expand the paramagnetic approach to much more complex molecular systems which could be tackled by multidimensional animal. What was a kind of annoying us was that the correlation between the solvent exposure of the correlation lysozyme in this case, and the exposure, atom exposure, was not very direct, because you can see here that for baried protons we could observe unattenuated cross peaks or very attenuated. So we said maybe it's because the paramagnetic interaction is something through space. So we have to not just give an analysis in terms of exposed or buried, but how atoms were inserted in the structure. For this reason, we decided to develop a method, a new algorithm, for calculating in a quantitative way the atom depth. What we found at that time was rather unexpected, that surface exposure have been well analyzed since the Lee and Richards work in 1971, but not much was done in terms of atom depth, because the first paper on this subject was a paper in 1999, and also that the atom depth was considered mainly as the distance between one atom and or the nearest water solvent or the nearest accessible solvent accessible point of the molecule. So always distance not related to the actual three-dimensional shape of a protein. So for this reason, we developed a new algorithm trying to evaluate the exposed volume we could design, we could calculate of a probing sphere centered on each given atom within the structure. Of course, it was important to understand which kind of size had to have the probing sphere, and we found the best way was the probing sphere which had a radius, the maximum radius, which made an exposed volume as 0 for the most internal atom of the structure. So in this way, we could define a ratio of the exposed volumes of all these atoms, of all the atoms of the molecule, of the protein, but not necessarily of the protein, any complex molecule, and this probing sphere. What the algorithm we named SADIC, which was kind of unfortunate because people trying to find the algorithm through the web before getting our algorithm was collecting a lot of junk. And it's possible now to use this algorithm going directly to the website of our lab, and it's possible to give or a PDB file homemade or giving directly the code, and you get a new file containing replacing the R values with the depth index I defined before. So happy about this idea of getting a quantitative evaluation of atom depth. We went back and see if we found a better correlation between paramagnetic attenuation and atom depth. And again, you can see that the data, well, part of the degeneracy was removed, but data was still scattered, meaning that Temple was snooping around the protein surface, but not in a linear way with the sulfate exposure. So something had to be favoring or preventing the access of Temple to the surface. Of course, if we had used, instead of our atom depth, the distance, the 2D atom depth, things were even worse because the degeneracy of the data was very bad. What we found is that with our system of calculating the atom depth, we could correlate in a reasonable way the proton-deuterium exchange rate. We could do this rather nicely with our criteria of atom depth, which was not possible to reach with the atom depth, the 2D atom depth. So this thing made us thinking a lot in terms that water actually proves in a very better way, comparing to Temple, the surface accessibility. And why? Because it's small and it goes wherever she lies due to the size. And so this correlation at the same time meant that water actually was giving troubles for the Temple accessibility to the surface because the hydration dynamics around the protein was actually the limiting or the favoring step for Temple protein interaction. So while we were trying to get additional information of this, and of course we used the epoxy spectroscopy for understanding water dynamics and see the time water was residing around the protein surface. Of course, we had the idea, why not, to put some temple in solution, and what we got as a side dish was that we were able to delineate rather precisely the location of the buried water molecule inside proteins. This approach has not been used very much. There are very few papers related to this approach, which I think is very good because knowing the presence in solution of internal water gives very important hints, for instance, in the field of enzyme, because enzyme looks like, on the basis of my experience, that close to the binding site, the active site, they have buried waters, because buried waters are used as a kind of lubricant for the flexibility which is necessary for the catalytic activity of the enzyme. So, overall picture is that temple delineates the surface exposure mainly of backbone amides which are not involved in intramolecular hydrogen bonding, which is again a very interesting feature, because this kind of amide protons are those which are involved in the binding of small ligands. And we did that for a series of proteins. Some other are not mentioned because the data are not published, but all in this paper was clear that the nitroxide could identify rather unambiguously the hotspots of the proteins. And talking about hotspots, this is a work I presented also in Florence in 2010, and was a kind of investigation was aimed in trying to design disruptor of protein-protein interaction. And while we were trying to design disruptor for this kind of interaction, which is very important because due to this dimerization of this protein and the interaction of the receptor, a signal comes out making proliferation, metastasis proliferation start. So, is a field very hot. And trying to figuring out where we could find binding site for a possible disruptor of the protein-protein interaction, we found that with again with temple, we could here I won't go into detail describing the spectra. There are spectra at two different pHs. They are rather different in some respect, and we could see that at one pH it's a binding site present, binding site for temple, which is not present at pH 7. And if we try to rationalize this finding, we could see that the binding site we found at lower pH is a binding site which is a transient pocket. So, why we can see transient pockets with this kind of approach? The answer is simple, because the interaction is very strong, the AES interaction is strong, so even if the population of the transient pocket is low, the effects is reasonable and can be defined through the NMR spectra. Last but not least is another application of temporary which has not been used by anyone apart of us. We studied a small RNA and we saw that the most perturbed signal were the signal of unpaired RNA base. So I think this would be a general strategy for understanding active sites of a small RNA. And maybe someone will do it in the future. Not me, because working with RNA it is bloody expensive and I wouldn't have ever money to have RNA double enriched in nitrogen, carbon, and so on. So, let's leave tempo. Something I did in the early, the end of the 70s and the beginning of the 80s was the heteronuclear overhauser effect. Heteronuclear overhauser effects, I think with the animation I will have problems because of this version of PowerPoint, but anyway, okay, because this shouldn't be overlapped. What we did, we developed a pulse sequence for getting selectively the overhauser effect between irradiated protons and carbons. In this way, we could have a very accurate environment of the irradiated protons. And this was something could give very powerful information for organic chemists for studying the subtle aspects of natural products, small molecule in general. Not many applications, again, in literature on this approach, which I think was very elegant and powerful, and such is life. But, so we went ahead, and one other thing I would like very much is combining surface plasma resonance, Biochimica, and nuclear magnetic resonance and molecular dynamics for obtaining information on the interaction of peptides and proteins. And what we did at that time was presented again, of course, at the 33rd conference in Brixen in 2003. And by combining the structural information we could get from NMR, the structure of the complex between bungal toxin and a variety of peptides, and the affinity, more than affinity, the kinetics of the binding of the peptides and the lifetime of the bound state. And these are standard results we can obtain through Biochimica. And molecular dynamics simulation, we could get a very accurate picture like the one I'm showing you. And I think also this was something very interesting, which was, again, not much considered by the literature, such as life. So, facing with a magnet quench, we had to be forced to move towards bioinformatics. And in this way, it was the time of SARS, you remember, 2003. Since we didn't have much to do, we started modeling the structure of the peptidoglycan protein of SARS with the students, and unexpectedly I obtained the fame, because, for instance, key refer to what I did. So my personal impact factor in for my barber, people fixing my car, all the people living in the village close to Siena were considering me much higher than before. At least this was a kind of pre-medal I got at that time. And of course, we were able also to publish the result because that structure was used to understand the evolution of the coronavirus. So we could, on the basis of our structure as the template, see where the mutation occurred and having an idea of how the virus evolved. So that was just the beginning. Now we are arriving at the very last part of our activity, which of course continues trying to define disruptors of protein-protein interaction for developing antitumoral drugs, getting rich and famous. But what is keeping my mind in these days is what I'm going to tell you. Now, proteins interact with other proteins within a molecular mess. What David Goodsell painted, and you can see, is just a very simplified picture of what happens inside the cell. So, my story with the temple, which probes the surface of proteins, the accessibility story, temple explained to me in 20 years or so, made me think that what is known at this point is not sufficient to understand the fine mechanism of protein-protein interaction. Because, for instance, first says that there are random translation of proteins which make collisional events favoring the complexation, protein-protein complexation. More precisely, the group of Blandel is considering the formation of encounter complexes which go towards the protein complex, but still remains the mystery of how two proteins are close enough for starting this story of evolution of encounter complexes. Not much has been done in these days, apart a very elegant study, of course, using paramagnetic relaxation enhancement but the probe in this case is bound to one protein, and so it was possible to see the interaction of the two proteins and getting a lot of information on the dynamic of approach. But this was something done in a test tube with no other interference with all the mess, the molecular mess. So, what I decided to do is try to use the approach of bioinformatics that is comparing huge amount of data, extracting features, patterns. And what I decided to compare were the structural features of proteins whose structure is known and well stored in the protein data bank. Of course, we didn't use the complete set of protein in the data bank. At that time there were 90,000 structures, so maybe 85,000 structural proteins. I decided to put filters And I used, not for betraying our favorite NMR approach, but just to have proteins with a compact structure, because I was interested in compact features of compact structure, not perturbed by the interaction with other molecule, proteins or ligands. So, okay, this is the list of filters we put, and in this way we came out removing identical structure at 95%. We arrived at 2,410. Now, using the same kind of structural search, the structure 2,600 something. But this data set, protein data bank, was not too bad, because you can see that the amino acid content in the data set resembles very much the amino acid content in Swiss prot, that is 600,000 sequences, and also the variety of complexity of our data set was not too narrow if compared with the one of Swiss prot again. So what we did, having these 2,400 proteins, we tried to see the amino acid contents of structural layers, and that was possible because with SADIC, the atom depth algorithm, we could classify atoms in terms of atom depth. So actually it was kind to remove the layers of the onion, and we could analyze layers by layers the amino acid contents of the proteins of our dataset. And what happens is that we see that some amino acid changes their abundance from the inner the inner layer to the outer one, and of course this is the case of the hydrophobic amino acid. Interesting to see that there are amino acids which prefer the second or the third layers, and maybe we could be interesting to give a look a bit closer to this aspect. And going to the polar ones, was possible to see that the lysine and glutamate had the most abundant percent in the outer layer. But and this is rather obvious again, we could make a quantification of this, and coming out the glutamates and lysines are the most abundant. This is not a real achievement. Was an achievement, I think, finding that the adjacent position of lysines and glutamates were again lysines and glutamates, meaning that the surface of proteins hosts a large variety of charged side chain which are talking each other. At least the glutamates and lysine did that. So going to the conformation of proximity of a charged group, the thing is like the one we can see in this animation obtained from molecular dynamic simulation. You can see that, you cannot see, but okay, no problem, I can do it. They are part of this molecular dynamics simulation where we don't have actual changes of net charge, for instance, in here, but in other parts you can see that where we have sometime red, then soon after we have blue, and so. So, meaning that the surface of the protein has a very peculiar behavior in terms of interaction of charges. So, we could do many things, but okay. With the PowerPoint 2010, this would be front door. So, you can imagine what is in there. So, we decide to use atoms for probing the approach of charged side chain, and following these approaches, we could extract, making a suitable threshold, the complete charge network for ubiquitin. So we could see that the ranking of this intercharge approach was different, and I don't know, it will appear. Well, okay. In here was an arrow pointing to aspartic 58, which is, believe me, on the binding part of ubiquitin. And that made us think, because the binding part of the protein had a charge not perturbed by neighboring charges. That was interesting. While all the others were dancing freely, because apparently they didn't have a role. So everything works for ubiquitin. We tried the same kind of approach with a much more complex enzyme. It's a chenolytic enzyme, 594 amino acid big, and we repeated that kind of approach, and we found that the 851 charged residues were interacting a lot with each other, apart from a small number of charged residues, like this one, which had ranking equal 0. So they were rather isolated. What is interesting is that again, one of these is just in the rim of the active site. So this lysine 323 is not perturbed by other charges, because it has to call the substrate inside the enzyme. And we found this kind of thing rather interesting. I don't know what is going on now. And, no, maybe didn't go too bad. Going back to ubiquitin, we saw that, if we consider the environment of lysine 33, we see, and of course we can analyze the distance between this carbon and the lysine nitrogen through the molecular dynamic simulation, and we see here, maybe, okay, that these charges are approaching back and forth each other. For, on my knowledge, opposite charge moving, approaching, creates electromagnetic radiation. Now, the rate of this radiation has to be the one which is typical of the motion of side chains, and we know for ubiquity that, again, nuclear magnetic resonance was fundamental in this respect, because the authors of this paper found the range of motion of these charged side chains, and we are in the range of terahertz. Now, have these electromagnetic waves a role in the long-distance protein-protein interaction? I personally think my answer is yes, but I may be very wrong. In fact, I tried to submit as an hypothesis to FEPS letters this contribution of mine, and I was crucified because my physics, the description of the effect I'm telling you in terms of physics was very gross, so they said, okay, study physics and come back. And just to prove what I'm saying, I would need experiments and terahertz spectroscopy, see the title, and NMR, for sure, trying to investigating the effects of mutants with this, the binding affinity on protein complexes, and again, surface plasmon resonance will be important in this respect. But of course, before designing an experiment, I would need to go to a quantitative description of this effect, and the quantitative description of this effect can be done with quantum electrodynamics. And quantum electron dynamics is something I won't be able at this age and to go through by myself. So the help of physicists will be important in this respect, because thinking to quantum electrodynamics make me think to the infinity of Giacomo Leopardi and floundering with sweet in such a sea. And thank you all. I don't know if now we'll come here to take back the medal.
Just like to have a picture together with you, of course.
Okay.
Thank you very much for your very nice review of your whole production. It was really interesting to see. It makes us even more proud to have awarded this medal to you.
It's mine.
It's yours, yes, of course. And traditionally, we haven't any question for the awardees of the medal. But I have a question, actually, about the key journal. Did the journalists know actually anything about your work? What did they ask you?
The FEPS letters.
No. The key.
Well.
I know, it's strange. It's an awkward question.
You were talking in English when I said.
No, it's not key.
No, that was a funny story.
Who? The paper who?
Because at that time I was a kind of famous because the Sole 24 Ore made an article about our work, and also several specific journals for divulgating science. At that time, it was a Mondadori magazine. It was called The Macchina del Tempo. I was supposed to publish my interview, but the editorial board decided to send me back to Key instead of The Macchina del Tempo. But it was very good. It was very good, because still now, when I take my car, fix it for some reason, professor.
very well. So the other point is the last one because we are a bit late here. I was really impressed by what you did after the quench. Yeah. So a quench can turn into something good for science. So you know, I work for a vendor. So next time some of my customers tell me they have a quench, I tell them to switch to bioinformatics. Okay, right. So okay, we thank again. Yeah, thank you very much.